Hello, my name is Roger Hernandez Mercado, and I'm presenting on high-wattage IoT botnet attacks on power grids and energy markets. To begin, I'd like to start with acknowledgements. The first paper I will be discussing is Black IoT. IoT botnet of high-wattage devices can disrupt the power grid, authored by Salih Sultan of Princeton University, Pratik Mittal of Princeton University, H. Vincent Poor of Princeton University. This paper was presented at the 27th Cybersecurity Symposium in Baltimore, Maryland, August 15th through 17th of 2018. The second paper I will be discussing is MAM IoT, Manipulation of Energy Market Leveraging High-Wattage IoT Botnets, authored by Tauhid Shikari of Georgia Institute of Technology, Celine Irvine of Georgia Institute of Technology, Alvaro A. Cardenas of University of California, Santa Cruz, and Rahim Baya of Georgia Institute of Technology. This paper was presented at the 27th ACM Conference on Computer and Communication Security in Seoul, South Korea, November 15th through 19th of 2021. The third paper I will be presenting on is MAD IoT 2.0, Modern High Wattage IoT Botnet Attacks and Defenses, authored by Tauhid Shikari of Georgia Institute of Technology, Alvaro A. Cardenas of University of California, Santa Cruz, Rahim Baya of Georgia Institute of Technology, and this paper was presented at the 31st Usenex Security Symposium in Boston, Massachusetts, August 1st through 12th, 2022. The purpose and objectives of this presentation are to evaluate the real threat of IoT-based grid attacks. Black IoT proposed the concept of using high-wattage IoT devices to disrupt the power grid. MAM IoT demonstrated how coordinated high-wattage IoT botnets can manipulate electricity demand to influence wholesale energy markets for financial gain. And MAD IoT 2.0 demonstrated that modern power grids remain vulnerable to coordinated IoT load attacks. We will also analyze, critique, and compare each paper threat models, solutions, and methods, and propose a new research idea and defense strategies to mitigate these emerging threats. Before we begin our discussion about the papers, let's review some power grid basics. The power grid is divided into different sectors that are connected through substations. The voltage at generators is originally medium voltage. This generated power is then stepped up to a higher voltage level to be transmitted over long distances. This voltage level change is performed to reduce energy losses in transmission lines, and eventually the electricity is stepped back down to a medium voltage level by distribution substations near end users. Electric power also has two main elements, active and reactive power. Active power is the part that flows from the generator to the load, and reactive power is the part that is continuously flowing from source to load and is returning back to the source. Total demand for power is ever changing, and to preserve system stability and avoid any large-scale blackouts, the output power of generators must match the demand in real time. Some of the main controls to control power are the primary frequency controller, which adjusts generator output instantly to correct short-term frequency changes. The automatic voltage regulator, which regulates generator voltages by controlling reactive power. And the automatic generation control, which coordinates generator system-wide to restore frequency and power balance. Various protection schemes are used to protect the integrity of the grid. The table below shows the most common protection schemes used in power grid. When a major fault occurs, protection schemes automatically isolate the fault area of the grid to prevent total system collapse. This may cause localized outages but protects the rest of the network. UVLS and UFLS are the primary protection schemes observed addressing botnet IoT attacks. The first paper we'll discuss is Black IoT. First, we'll define botnet, which is a network of interconnected internet devices that are infected and remotely controlled by malware. The main motivation of this paper is due to the increasing trend in IoT high wattage appliances such as air conditioners, electric water heaters, and electric ovens, along with many others that consume large amounts of power. Numerous studies have also revealed that various vulnerabilities in IoT devices allow intrusion and command and control. And this was seen for the first time with the Marriott botnet, which compromised 600,000 devices and was able to launch a DDoS attack that showcased the collective effect of IoT vulnerabilities. For the threat model of this paper, some assumptions were made. First, that the attacker had access to a large-scale botnet of IoT high-wattage devices, and also that the attacker had the capability to turn the botnet devices on or off. The main threat model of this paper was the manipulation of the demand via IoT, or MAD IoT. The goal was, instead of targeting network bandwidths typical of botnets, it was to be leveraged to target electrical demand. Using a botnet evenly distributed across the grid to switch devices on and off simultaneously could cause abrupt demand fluctuations. This had the potential to destabilize the grid by causing significant frequency drop or rise, disrupting a black start, causing line failures and cascades, causing failures in tie lines, and increasing operating cost. For the experiment setup of the Black IoT paper, the attacks were simulated with Map Power and Power World simulators. A WSCC 9-bus system grid was modeled to evaluate frequency attacks. It included 9 buses, 9 lines, and 315 megawatts of demand. Also, the Polish grid data was used to evaluate power flow's impact. The year of the summer of 2004 peak was used, which included 2,736 buses, 3,504 lines, and 18 gigawatts of demand. Also, the summer of the 2008 peak, which included 3,120 buses, 3,693 lines, and 21 gigawatts of demand. And a normalized botnet size and botnets per megawatt was used for comparison. The first way that the Black IoT botnet was tested was on frequency disturbance. The objective was to manipulate grid frequency by changing electrical demand. The results that were seen was that generation was unable to match load changes by 20% and 30% during low inertia case. That grid frequency deviated from the range of 58.2 to 61.2 hertz, which is typical of US power grids. This caused disconnection of protective relays. The attack then succeeded with the use of 200 to 300 bots per megawatts, corresponding to around 60 to 90,000 high wattage bots. Another way that the botnet was evaluated was its effects on line failures and cascades. The objective was to trigger transmission line failures that can result in cascading power outage. The results seen were that 1% increase in electrical demand was enough to initiate cascading failures using Poland's 2008 power grid. The overload of a few transmission lines caused the power rerouting that further caused overloading of neighboring lines. In total, 263 transmission lines were able to be overloaded, resulting in an overall 86% system outage. One of the final ways that the Black IoT botnet was evaluated was its effects on the increasing operating cost. The objective was to increase operational cost of power grid through coordinated demand manipulation. The results seen were that coordinated demand caused grid operators to dispatch reserve generators to meet additional demand. Operating costs rose as demand increased, reaching 20% increase under worst case scenarios with only 5% demand increase. The attack succeeded with the use of 50 bots per megawatt, corresponding to around 1 million high wattage bots in total. Some of the key insights from the Black IoT paper were that it introduced the concept of manipulation of demand via IoT, for short MAD IoT. It demonstrated that IoT botnets can leverage consumer devices to disrupt power grids. However, some of its limitations were that it only leveraged public data that may not accurately reflect the power grid. It did not consider existing control mechanisms for minimizing effects of initial failure. It assumed that high wattage devices reached maximum capacity immediately. And it assumed that large number of bots that were needed to cause grid destabilization were located within the system boundary of the power grid. The next paper we'll be discussing is the MAM IoT paper. The Black IoT paper showed that a coordinated attack using a high wattage botnet was able to abruptly disrupt power grid operations. MAM IoT, the first market manipulation attack, introduced the concept of leveraging a high wattage botnet to manipulate the market. The paper explored if market manipulation can generate financial gain or inflict economic damage while remaining undetected. The reason this concept was explored was due to the large energy consumption in the U.S., which totals around $220 billion in transactions. Another reason that this was explored was the fact that demand and electricity costs can be very volatile, allowing the opportunity for market manipulation. For the MAM IoT threat model, some assumptions were made, similar to the Black IoT paper. First, that the attacker had access to a large-scale botnet of IoT high-wattage devices. And second, that the attacker had the capability to turn the botnet devices on or off. For the manipulation of market via IoT, there were two different types of attacks that were explored. The first type was the goal was to manipulate the electricity market and profit financially from the attack. The attacker submits bids or purchase orders and then commands the botnet to act. For the second type of attack, the goal was to make the market as inefficient as possible and thus cause economic damage to operators of the power grid. The attack begins with the market participant, such as a power plant owner, who also controls a botnet of high wattage IoT devices like air conditioners or electric water heaters. At the start of the market interval, the attacker sends commands to the compromised devices, causing a small increase or a decrease in electricity demand. However, unlike the Black IoT paper, these changes are intentionally kept small enough to avoid detection. The artificial demand changes influences the market clearing process. Since electricity prices are determined by supply and demand, even a slight increase in demand may require more expensive generators to be dispatched, increasing the market clearing price. The attacker then benefits from this price change. If they own a generation asset, they receive a higher revenue for the electricity they sell. And if the attacker is a nation state, the objective is instead to force the market to operate less efficiently, increasing the cost for utilities and consumers. The key idea is that the attack does not attempt to cause a blackout. Instead, it subtly manipulates demand to influence electricity prices while remaining within normal load forecasting errors, making the attack difficult to detect. To evaluate the feasibility of the MAM IoT attack, the researchers used real-world electricity market data from two of the largest wholesale electricity markets, the New York Independent System Operator, or NYISO, and the California Independent System Operator, or CAISO. For both markets, they analyzed 1 year of historical data from May 2018 through May 2019. This included real-time market prices and system demand data. The New York market represents approximately 300 million megawatt hours of electricity per year, while the California market represents approximately 156 million megawatt hours per year. An important parameter in the study is the day-ahead forecast error band. Grid operators expect actual demand to differ slightly from forecasts due to normal uncertainty. In this dataset, the allowable error was approximately 580 megawatts for NYISO and 2,265 megawatts for CAISO. The attackers intentionally kept their demand manipulation within these normal forecasting error bands, allowing the attack to influence market prices while appearing as ordinary fluctuations in electricity demand. The first attack considered in this paper is a profit-seeking market participant, such as a power plant owner. Rather than trying to cause a blackout, the objective is to slightly manipulate electricity demand so that wholesale electricity prices increase. Since the attacker owns generation assets, they benefit from selling electricity at the higher market price. The researchers found that with approximately 200,000 compromised IoT devices, each consuming about 3 kilowatts, the attacker could earn an additional $150,000 in profit per day in the New York electricity market. This represents roughly a 30% increase in profit compared to normal operations. If the attack were carried out for just 100 days per year, it could generate approximately $15 million in additional annual profit. Perhaps the most important result is the attack remained within the normal day-ahead forecasting error, allowing it to influence electricity prices while appearing as normal variations in demand. This makes the attack significantly more difficult to detect than the abrupt demand changes introduced in Black IoT. The second attack represents a nation-state or economically motivated adversary. Unlike the first attack, the goal here was to not make a profit, but rather to make electricity market as inefficient as possible and increase operating costs. Again, the attacker uses approximately 200,000 compromised high-wattage IoT devices to make small, coordinated changes in electricity demand. These changes force the market operators to dispatch more expensive generators to satisfy the additional demand. The results show that on the demand side, the attack increased electricity costs by approximately $3.5 million per day in California and $5 million per day in New York. On the generation side, operating costs also increased by approximately $2.8 million per day in California and $2.9 million per day in New York. Just like the first attack, these demand changes remained within the normal forecasting error bands, allowing the attacker to inflict significant economic damage while avoiding detection by standard market operations. Overall, MIMIoT makes two important contributions. First, it expands on the original MAD IoT attack model by introducing the concept of manipulation of market via IoT, demonstrating that coordinated IoT botnet can be used for economic attacks rather than simply disrupting the power grid. Second, it shows that small, carefully timed demand changes can influence wholesale electricity prices while remaining within normal forecasting error, making the attack much more difficult to detect than the abrupt demand changes presented in Black IoT. There are, however, several limitations. This paper assumes that the attacker had detailed knowledge of electricity market operations and can precisely time the demand manipulation to coincide with market settlement intervals. The evaluation is also based on historical market data and simulations rather than testing against a live operational power grid. Like Black IoT, it assumes compromised high wattage devices can immediately reach their maximum power consumption, which may not always reflect real appliance behavior. Finally, while the authors propose non-intrusive load monitoring as a promising countermeasure, they do not implement or evaluate its effectiveness. This leaves an open research opportunity for developing practical detection and prevention mechanism. MAD IoT 2.0 builds directly on the findings of the previous two papers. The original MAD IoT, introduced in Black IoT, demonstrated that a coordinated botnet of high wattage IoT devices could create sudden demand spikes capable of destabilizing the power grid. However, follow-on research, particularly the paper Not Everything is Dark and Gloomy, argued that these attacks were less severe than initially thought because modern power grids already employ sophisticated protection mechanisms. These protections can often mitigate or completely neutralize large random demand surges. Instead of distributing the botnet evenly across the grid, MAD IoT 2.0 assumes the attacker has knowledge of the power grid and can identify its weakest locations. By targeting these vulnerable nodes using real-time grid information and voltage stability analysis, the attacker can maximize the impact of the botnet while bypassing many of the protection mechanisms that stopped the original MAD IoT attacks. Unlike the previous papers, MAD-IoT 2.0 assumes the attacker is grid aware and gathers information before launching the attack. The process begins with an offline reconnaissance stage where the attacker learns the architecture of the target power grid. While utilities don't publicly release detailed grid models, the paper points out that an attacker could infer much of this information through phishing, social engineering, or even publicly available mapping services such as Google Maps. Next comes the first online stage, data acquisition. Here, the attacker collects real-time operating data from publicly available sources, such as ISO websites or financial platforms like Bloomberg. These sources provide information such as power generation, electricity demand, and system conditions, typically updated every 5 minutes. Finally, in the system analysis stage, the attacker analyzes this information to identify the weakest nodes in the power grid. Using voltage stability analysis, they determine which locations are most susceptible to instability and therefore provide the greatest impact for the available botnet. This is a key innovation of MAD-IoT 2.0. Instead of attacking the grid randomly, the attacker uses real-time information to select the most vulnerable targets, making the attack significantly more effective while requiring fewer compromised devices. After collecting real-time grid information, the next step is to determine which nodes are the most vulnerable to an attack. Rather than attacking randomly, MAD-IoT 2.0 uses voltage stability analysis to rank each node according to how close it is to voltage instability. The paper evaluates two different methods. The first is voltage magnitude, or index 1. This is a simpler approach and only uses the measured voltage at each node. Since grid operators try to maintain voltages between approximately 0.95 and 1.05 per unit, nodes with lower voltages are assumed to have a smaller stability margin and are considered weaker targets. The second method is modal analysis, or index 2. This approach uses the reduced Jacobian matrix from the power flow equations to calculate the voltage to reactive power sensitivity at each node. Although this requires more computation and more detailed knowledge of the grid, it provides a much more accurate estimate of which nodes are truly vulnerable. The researchers ultimately found that Index 2 produced better attack predictions, allowing the attacker to identify weak locations much more accurately than simply relying on voltage magnitude alone. Once the attacker has identified the weakest nodes, the next step is to determine whether an attack is actually feasible with the available botnet. This paper describes a four-step process. First, the attacker updates the load at the target nodes based on the number of compromised IoT devices under their control. Secondly, they perform an AC power flow analysis to determine how this additional demand affects the operating point of the grid. Third, they recompute the reduced Jacobian matrix and the voltage to reactive power sensitivities using the updated system conditions. Finally, they evaluate the VQS modal index. If the index is negative, the attack is considered feasible because the system is close enough to voltage instability. If it remains positive, the attacker simply waits for the next 5-minute update of public grid data and repeats the analysis. This continuous monitoring allows the attacker to launch the attack only when conditions are most favorable, significantly increasing the likelihood of success while minimizing the required botnet size. Because evaluating these attacks on a live power grid would be extremely risky, the researchers conducted all experiments using simulation. They used DigSilent Power Factory, an industry standard power system simulation tool capable of modeling generator dynamics, protection systems, and power flow behavior. The primary test system was the IEEE 39-bus New England power system, which is a much more realistic model than the smaller test systems used in earlier work. It contains 39 buses, 32 transmission lines, 24 transformers, and 10 generators, with a total base load of just over 6,000 megawatts. For comparison, they also evaluated their approach on the IEEE 9-bus system, which had been used extensively in previous research. This smaller system consists of 9 buses 6 transmission lines, 2 transformers, and 3 generators with the base load of 350 megawatts. Using both test systems allowed the researchers to compare their approach directly against prior work while also demonstrating that the attack remained effective on a large and more realistic power grid. For the simulations, the researchers modeled the power grid over a 24-hour period, assuming that public grid data was refreshed every 5 minutes, which matches the update frequency of many ISO websites. The attacker was assumed to control a botnet of 150,000 high-wattage IoT devices, with each device capable of consuming approximately 3 kilowatts. Across the 39-bus test system, this equates to roughly 3,850 compromised devices per node. Based on residential electricity usage, the authors estimated that approximately 52,000 high-wattage IoT devices would realistically exist within the New England power grid, providing a practical basis for their assumptions. Finally, the researchers evaluated the accuracy of their attack predictions methods using standard binary classification metrics. They defined true positives, true negatives, false positives, and false negatives, allowing them to calculate performance metrics such as precision, recall, and ultimately the F1 score, which they use later to compare their approaches against previous work. One of the major improvements in MAD IoT 2.0 is the realism of its power grid model. Earlier work included Black IoT simplified many aspects of the power grid. In particular, they did not fully model the controllers and protection systems that utilities rely on to recover from disturbances. As we discussed earlier, follow-up research showed that these protection mechanisms can successfully mitigate many random IoT demand attacks. To address this limitation, MAD IoT 2.0 incorporates detailed models of generators, controllers, dynamic loads, and protection schemes into its simulations. This is important because these concepts determine how the grid responds after a disturbance. Ignoring them can produce unrealistic results or overestimate the impact of an attack. By modeling these systems more accurately, the researchers were able to evaluate whether a targeted grid-aware attack could still succeed against the same protection mechanisms that defeated the original MAD IoT attack. To evaluate their approach, the researchers compared MAD IoT 2.0 against the methods proposed in Black IoT, and Not Everything is Dark and Gloomy. They use the F1 score, which combines precision and recall into a single metric to measure how accurately each method predicted successful attacks. The earlier approaches achieved 100% recall, meaning they did not miss any successful attacks. However, they also produced a large number of false positives, incorrectly predicting that many attacks would succeed when they actually would not. MAD IoT 2.0 significantly reduced the false positives while maintaining a high detection rate, resulting in the highest overall F1 score. The researchers also found that Index 2, which uses modal analysis, consistently outperformed Index 1, confirming that a more detailed voltage stability analysis provides a much more accurate way to identify vulnerable nodes. Finally, they repeated the evaluation on the smaller IEE 9-bus system and observed similar trends, showing that the approach generalized across different power system models. Next, the researchers examined how the size of the IoT botnet affected the success of the attack. As expected, increasing the number of compromised devices improved the attack success rate. Larger botnets allowed the attacker to manipulate more electrical demand and more effectively target vulnerable nodes. However, the results also showed diminishing returns. Once the botnet reached approximately 150,000 devices, the success rate began to level off. Beyond this point, adding more compromised devices provided very little additional benefit because the attacker had already reached the practical limits of the attack. The researchers also repeated the experiment on the smaller IEEE 9-bus system. As expected, it's a much smaller botnet, around 5,500 devices. was sufficient to achieve similar success. This demonstrated that the number of compromised devices required depends on the size and characteristics of the target power grid. Smaller grids require fewer devices, while larger grids require proportionally larger botnets. This figure compares how the power grid responds during attacks generated by previous methods versus MAD IoT 2.0. Looking first at the attacks from Black IoT and the earlier approaches, we can see that the grid controllers and protection schemes are able to recover the system. Although the attack initially disturbs the grid, the voltage and frequency eventually return to normal operating conditions. However, the results are very different from MAD IoT 2.0. Because the attacker specifically targets the weakest nodes in the system, the disturbance is much more severe. The voltage continues to collapse and the system frequency fails to recover, even with the existing protection mechanisms in place. This demonstrates the paper's key findings. Modern protection schemes are effective against random demand attacks, but they can still be defeated by a well-informed grid-aware attacker that exploits real-time system conditions. After demonstrating that MAD IoT 2.0 can bypass existing protection schemes, the authors proposed an updated defense strategy shown here in Figure 16. The key idea is to enhance traditional protection mechanisms by incorporating voltage stability information into the decision-making process. Instead of relying primarily on frequency-based protection, the updated scheme prioritizes load shedding in areas experiencing rapid voltage decline. As shown in the figure, this approach allows the system to recover. The voltage no longer continues to collapse, and the system frequency stabilizes after the attack. This demonstrates that while intelligent grid-aware attacks can overcome existing protections, adaptive protection schemes that account for voltage stability can significantly improve the resilience of the power grid. In summary, MAD IoT 2.0 demonstrates that intelligent, data-driven IoT botnet attacks remain a serious threat to modern power grids. Unlike the original MAD IoT attack, which distributed compromised devices randomly, MAD IoT 2.0 uses real-time grid information and voltage stability analysis to identify and target the weakest nodes in the network. By doing so, the attackers were able to bypass modern power grid protection schemes, causing voltage collapse and cascading failures with fewer compromised devices than previous approaches. The paper also showed that while conventional protection mechanisms are effective against random demand attacks, they are much less effective against targeted grid-aware attacks. Finally, the authors proposed several defensive strategies, included adaptive protection schemes, limiting the amount of publicly available grid data, and using deception techniques to make reconnaissance and attack planning more difficult. Overall, the paper demonstrates that as high-wattage IoT devices become more widespread, protecting the power grid will require defenses that are just as intelligent and adaptive as the attackers. Looking across all three papers, we can see a clear evolution of high-wattage IoT botnet attacks. Black IoT introduced the idea that compromised IoT devices could be coordinated to physically disrupt the power grid through abrupt demand changes. The focus was on causing frequency instability, line failures, and cascading outages. MAM IoT built on the concept but changed the attacker's objective. Instead of causing outages, it demonstrated that small, carefully timed demand changes could manipulate wholesale electricity prices for either financial gain or economic disruption while remaining difficult to detect. Finally, MAD IoT 2.0 revisited the original MAD IoT attack after previous research suggested existing grid protections were sufficient. By introducing a grid-aware attacker that leverages real-time data and voltage stability analysis, the authors show that targeted attacks can still bypass modern protection schemes. From a technical perspective, each paper assumes that the attacker controls a large botnet of high-wattage IoT devices, but the attack strategy becomes increasingly sophisticated, from random demand manipulation to stealthy market manipulation to intelligent grid-aware targeting. Overall, these papers demonstrate how the threat has evolved from proving an attack is possible to showing how a knowledgeable attacker can maximize both physical and economic impact while evading existing defenses. After reviewing these 3 papers, one common theme emerged. All of the proposed attacks rely on compromising a large number of high-wattage IoT devices. The existing defenses primarily focus on protecting the power grid after the attack has already begun. Whether it's grid protection schemes, market monitoring, or adaptive load shedding, the response occurs after compromised devices have already started manipulating demand. In addition, MAM-IoT proposed non-intrusive load monitoring, or NILM, as a promising defense, but it did not implement or evaluate it. My idea is to shift the defense from the grid to the consumer's home. Instead of trying to mitigate the effects of thousands of compromised devices, we can detect abnormal appliances behavior at the smart meter, isolate suspected devices before they receive additional command and control instructions, and prevent them from participating in coordinated attacks. This approach benefits both the utility and the homeowner. The utility sees fewer compromised devices contributing to large-scale attacks, while the homeowner avoids unnecessary energy consumption and is notified that one of their smart devices may have been compromised. To address this problem, I propose a NILM-based intrusion prevention system, or NILM IPS. The system continuously monitors a home's electrical usage using non-intrusive load monitoring. Rather than placing sensors on every appliance, NILM identifies individual appliance activity by analyzing the home's aggregate power consumption. The detected appliance behavior is then compared against the household's normal usage patterns. If the system identifies abnormal activity that is consistent with a compromised high-wattage IoT device, it automatically blocks the device's outbound internet communication, disrupting command and control traffic while allowing the device to continue operating safely in a local mode. At the same time, the homeowner is notified that a device may have been compromised, and an alert can be sent to the utility. If multiple homes report similar events, the utility gains early visibility into a coordinated attack. The key benefit of this approach is that it stops the attack before it reaches the power grid. Instead of relying solely on grid-level protections, the botnet is gradually dismantled at the source, protecting both consumers from unnecessary energy costs and utilities from coordinated demand manipulation. These are the primary references used throughout this presentation. They include 3 research papers that formed the basis of my analysis, along with a reference explaining botnets for background information. That concludes my presentation. Thank you for your time and attention.